Okay, that's really an annoying voice, isn't it? Let me get my share screen. Okay, so let me just sort of remind you what we did last and look at an example or two, and then we'll go on to bigger and better things. So the last time we continued, we talked about continuous random variables. And basically, continuous random variable is one whose range is either an interval or a union of intervals. So then we realize we need to talk about a probability density function. And the probability density function has a property. Firstly, it is non-negative. Oh, sorry, I got that backwards. It's non-negative. And the total area under the curve, the sum of all the probabilities, basically, is equal to 1. That's an important idea. Remember, when we talked about a discrete random variable, we had a probability mass function. All the probabilities, of course, were greater than or equal to 0. And the sum of the probabilities equals 1. These are called the normalization criteria. And then we said, okay, then the probability that any random variable lies between A and B is just the integral from A to B of the density function. Think of the probabilities being distributed per unit length, say, we're in 1 dimension, 2 dimensions, per unit length. Well, if you multiply the probability density times the sort of the length of the interval, that gives you the probability over that interval. And the other thing to observe, for a continuous random variable, the probability that x equals a particular value must always be 0. Effectively, if you look at your, suppose you have some density function like so. Here's A, here's B. The probability of a point happening, say at C, is 0 because there's no area swept out. Then I define the cumulative distribution function. There'll just be the probability that x is less than or equal to x, which mathematically, for a continuous random variable, let's change the dummy variable to t here. And typically for a continuous random variable, if you plotted the CDF versus x, it starts off somewhere at -infinity at 0, and then it's always increasing, ultimately always increasing until you get a final value of 1. Notice that's different from a discrete random variable. For a discrete random variable, what happened? It started at 0, and then you got these jumps, and ultimately you got to 1. A discrete random variable, the CDF was always right continuous. There was always a jump at the left endpoint to the right endpoint. And in fact, we know for a continuous distribution, this is equal to f of b minus f of a. More generally, for any distribution, for a discrete distribution, this is true. But notice, if I included or excluded the a here, it doesn't make a difference for the continuous distribution because the probability at a single point is 0. And then I said, okay, well, we could then define the expected value of a random variable. Now, instead of a sum, we have an integral. And in fact, more generally, if we have any function, this is lotus. Then, of course, the variance has the same definition as before, except to find e of x squared, you have to integrate. The moment generating function is e to the tx. And substituting in here, you see that's just the integral from minus infinity to infinity of e to the tx f of x dx. And then I introduced two very important discrete random variables. I looked at the uniform distribution. And the uniform distribution essentially says, if you have any 2 points A and B, the density function is a constant. Now, what must that constant be? Well, if the total area is to be 1, we know the length of this interval is B minus A. So in order for the area under this rectangle to be 1, f of x must be 1 over the length of the interval. And we showed for this density function, firstly, f of x is just x minus a over b minus a between a and b. It's 0 elsewhere. We also showed that e of x is the midpoint of this interval. And we showed v of x is the length of the interval squared over 12. So there's one distribution we talked about. And basically, if things are equally distributed, for example, I think I gave you an example the other day, if the train is just as likely to come at any time between 12 and 12:15, then that's a uniform distribution. So if I, for example, if the train schedule, a train is just as likely to come anywhere between 12 and 12:15, the probability it comes from 12:07 to 12:09 is just the length of this interval, which is 2 minutes, over the 15-minute interval. Why is that? Because we showed if we have a uniform distribution from A to B, and we have this interval C to D like so, the probability that x is between C and D is the length of this subinterval over the length of the entire interval. You can actually prove that using the definition, but that's what's so nice about it. That's why it's uniform. And then I defined the exponential distribution with parameter a. F of x was defined to be and a is greater than 0, of course, minus ax if x is greater or equal to 0 and 0 elsewhere. And I showed that for this distribution, f of x, the cumulative distribution function, excuse me, hello? The cumulative distribution function is just 1 minus e to the minus ax for x greater or equal to 0, 0 elsewhere. I believe I showed e of x turned out to be 1 over a, and v of x turns out to be 1 over a squared, if I remember correctly. Okay, and I also found the moment generating function for this function to be, what was it? A over, what was it? T minus x? I don't remember what it is. I'll have to derive it again. A minus t. In fact, I got this first, and then I showed you by taking the derivative evaluating at 0, we get e of x. Taking the derivative, second derivative evaluating 0, we get e of x squared. I want to do an example for you.
I have a question.
Yes.
For the moment generating function, so I understand how it's connected to ex and ex squared. However, I'm still not sure what the moment generating function actually means. Like, what does that tell us?
What it does is it's a function we rigged up, Tatiana, that if you think of it as a series, each term in its series is one of the moments of the random variable. That is, if you recall, when I looked at the series for m of t, it turned out to be 1 plus mu t plus mu 2 t squared over 2 factorial, and so on. So it's really an infinite series. That's one way of looking at it, if you expand it. And each coefficient, notice this is e of x, this is e of x squared, it generates all the moments of the random variable. Remember, e to the x to the k was called the kth moment. And this is how, by looking at this series, this is how we prove, for example, that firstly, you see that m of 0 is 1. If you differentiated this, you see m prime of 0 is the mean. And similarly, if you take the second derivative, you get u2, which is e of x squared. So it's a convenient function that generates all the moments. So if we have the moment generating function, by taking its first derivative, we can get the mean. By taking the second derivative, we can get e of x squared, and thereby we can find the variance or the standard deviation. Okay?
Mm-hmm.
All right.
Thank you.
So now let's look at it. And so what I did for the exponential function is I first showed by an integration, by an improper integration, using this result, which gives you minus infinity, infinity, e to the tx, e to the alpha x dx, put these together and write this as e to the minus, this was minus, I'm sorry, a minus t x dx, and integrate this. This gave me the moment generating function, what I say was before, over a minus t. And once I had this, it was easy to differentiate this with respect to t. Okay, two examples before we go on to new stuff. Example number one, I stole this example from the Ross's book on probability. And here's a problem. I changed it a little bit, but effectively it shows up there. It's an interesting problem. It says, a rope of length L is cut at some point which is uniformly distributed over its length. Okay. Now it turns out that this row, and let's suppose there's a knot at some point on the row. At some point P on the rope. So I have this rope of length L, and I'm going to cut it at some point, and I'm telling you I'm cutting it, the point at which I cut it is uniformly distributed over the length. So I'm telling you the PDF is 1 over the length. So now the question is, what is the expected length of the piece that contains the knot? So at first, this looks like it's a hard problem, but it's really very simple. So I'm going to let X be the point at which the rope is cut. And since we're told it's the point at which we cut is uniformly distributed, I know that PDF is just 1 over the length okay, that's my PDF. And it's 0, of course, elsewhere. Now, here's what could happen. There are two cases, so let's be careful. The problem, by the way, let L of X equal the length of the piece containing the point, the knot, at P. So the problem is to find the expected length of this piece. That's the problem. And by the way, we know by definition, but we have to be a little careful here, this is just L of X times F of X dx. But let's be careful. So what could happen? I want to show you there are two cases. So here's my length of rope. And let's suppose I cut it here. And this is the point P. So in this case, this is the length L of x, right, is equal to x. So if x is to the right of P, L of x is just equal to x. On the other hand, if this is x and this is P, well, this distance is x, then this distance is L minus x. So if x is less than P, then then L minus x is the length of the piece. So now, notice we can break this integral up. We notice nothing happens until we get to 0. So I can go from 0 to P, and between 0 and P, well, let's break it up like so. F of x, remember, is 1 over L. Plus from P to L of L of x times 1 over L dx. Okay, let's take out the 1 over L. Now on this first interval, x is less than P, right? We're integrating all x values between 0 and P. When x is less than P, the length is L minus x. And from now over this next interval, x is larger than P. And when x is larger than P, this is equal to x dx. The integration is pretty straightforward. Lx minus x squared over 2, remember L is a constant, from 0 to P, plus x squared over 2 from P to L. This gives me 1 over L, LP minus P squared over 2, plus L squared over 2 minus P squared over 2. And I could rewrite this as just 1 over L times L squared over 2 plus P times L minus P, if you like. So there's the expected length. So you might ask yourself, by the way, you notice I showed you this because it was a little tricky to figure out what L of x was here because there were two cases. Now, a problem one might ask in calculus is where should P be? Where should the knot be located if you want to maximize your expected value? By the way, notice I can write this piece here as PL minus P squared. So if I want to maximize the expected value with respect to P, we alter calculus, take the derivative, I get L rather. I'm differentiating with respect to P. I get L minus 2P. This will equal to 0 when P is equal to L over 2. So this says if the knot was at the midpoint of the rope, then the expected value of the piece containing P is maximized. Let's go to the silly question. So I want to do that one example for you to just show you how problems can come about and what weird kinds of problems can happen. This was a tricky problem, that's why I did it. And now I want to show you a relationship between continuous and discrete random variables. So I want to go back to the Poisson for a moment, and then we'll move ahead, okay? So the Poissons, I want to consider the following example. Let's suppose the number of automobile accidents at some intersection is, say, A accidents per week. Okay. So let's let X equal to the number of accidents in T weeks. Well, then if we have A accidents in 1 week, then we have AT accidents in 2 weeks, right? So here's our Poisson constant. So the probability that I get exactly K accidents in T weeks would equal to lambda to the K, e to the minus lambda over K factorial. But notice in this case, lambda is equal to alpha, I called it A rather, AT. So there's nothing new here. By the way, in the text, I probably may have called this X of T, but I don't really have to. So the number of accidents occurring in any intersection during any fixed period of time is clearly a Poisson distribution. Okay, so now let me ask you a different question because I want to show you an interpretation of the exponential distribution. I want to remind you, by the way, for the exponential, if we go back a little bit, I want to remind you that for the exponential, f of x is equal to 1 minus e to the alpha x. And by the way, I forgot to tell you, for any PDF, you can always recover from the CDF. I want to remind you that f prime of x, the derivative of the CDF is always the PDF. Okay, just a reminder of that. So now let's get back to this problem. Let's let t equal to the time in weeks until the next accident. Notice, whereas x was a discrete random variable, the time is a continuous random variable. The time could be anywhere between at any instant of time. So it's clearly a continuous random variable. Now, t will be greater than little t if and only if there are no accidents in the next t weeks. Now that means the probability that there are no accidents in the next t weeks is equal to the probability that x equals 0. Remember, x was the number of accidents in k weeks. So the probability there are no accidents in next t weeks is 0. But we know if I set right up here, if I set k equal to 0, that gives me this is equal to just e to the minus at. And by the way, the complement p of t less than or equal to t, therefore is 1 minus e to the at. But by definition, this is the CDF f of t. Now, whose CDF is this? This is the CDF for the exponential distribution with parameter alpha. That means if you have a Poisson distribution, the waiting time between accidents is a continuous distribution because it's being measured in time. And it's exactly the exponential distribution. That's a really cool thing. And I wanted to point that out to you. I do it a little differently in the text, not much so. So if one wants an interpretation of the exponential distribution, one can think of it as being the waiting time between events. Okay, so that completes what I wanted to say in section 3.1. I do a very nice example that you should read in example number 11. It's a very simple example. It's a nice example of exponential distributions as well. Do use it. It turns out that the CDF is often very useful for exponential distributions. Okay. Now, I want to talk about section 3.2 now. Anybody have any questions so far? Nope? Okay, good. So note, by the way, for the exponential, f of t equals 1 minus e to the minus at is very useful. And by the way, the exponential is the continuous analog of the geometric distribution. Remember, for the geometric distribution with parameter p, we showed that e of x for the geometric was 1 over p. For the exponential, we found it was 1 over a. I think we found for this was what was it? Was this 1 over p? I don't remember what it was. I remember, what was it? V of x what was the v of x? Q over p squared. For however, over here we got 1 over a squared. Remember, the geometric had what we call the memory list property. The exponential has the same property. That's an exercise that I give you. It's easy to prove. You might want to look at that. Okay. Section 3.2. Okay. In section 3.2, I also talk about mixed random variables. I'm not going to do that in this course. That's really for a more advanced course. I'm not going to do mixed random variables because I don't have the time. And it's a little trickier, and I don't want to spend time on it. I will talk about change of variables and maybe uniform distributions in higher dimensions. So I begin with an example. That is, so I want to consider how we change our variables. So consider the following example, which I can't read because I don't have my glasses on. Okay. So I'm taking example 1 from the text. Suppose I have a random variable x whose f of x is as follows. It's equal to 1/8 x between 0 and 4, and everywhere else it's 0. And I make a change of variables. I say, here's a new random variable y, which I'll call some function of x. And I say this is equal to 4 times x minus 2. I want to find the PDF of this new random variable. By the way, observe, if x goes from 0 to 4, when x is 0, y is equal to what? -2, right? Plug 0 in here. And when x is equal to 4, y is equal to 16 minus 2, which is 14. So we already know that y will be between -2 and 14. Okay, let me just make sure. Okay, I had that here. And now, of course, you'll see it's going to be 0 elsewhere, because since x is only defined between 0 and 4, y will only be defined between -2 and 14. So here's how we can find, so let's let the CDF of y be g of y. So g of y, by definition, is the probability that y is less than or equal to little y. That's how we're going to do it. We're going to work with the CDF. By the way, before I do anything else, I need a reminder. Remember the chain rule? If u is some function of x, and you want to find the derivative of f of u with respect to x, the chain rule says you take the derivative with respect to u and multiply by du dx. Or you might have seen it as g prime of u. So f is some function of x, right? Times du dx. That was a chain rule from Calculus 1. And I want to remind you of that because I'm going to need that very shortly. Okay, so again, g of y is the probability that y is less than or equal to little y. But we're being told here that y is equal to 4x minus 2. So I can rewrite this as p of 4x less than or equal to y plus 2, or p of x is less than or equal to y plus 2 over 4. So I have that g of y is equal to p of x less than or equal to y plus 2 over 4. Now remember, the PDF of x is defined to be the probability that x is less than or equal to little x. So we look at this, this is telling us that g of y is equal to f of y plus 2 over 4. Okay? So let's differentiate this. Let me just make sure I'm following what I did in the text here. Okay. So let's differentiate this. So if I differentiate this with respect to y, and by the way, let me call this for a moment u. Okay? Then by definition, the derivative of the CDF is the PDF. And by the chain rule, if I'm differentiating this with respect to u, this gives me f prime of u times du dx, du dy, I'm sorry. I'm differentiating with respect to y here. So I have g of y. Now the derivative of the CDF is the PDF. And notice u is equal to 1/4 y plus 2. So du dy is equal to 1/4. So I have g of y equals f of u. Remember what f of x was. F of x was 1/8. Is that right? Something's not right. So this is f of I'm sorry, I made a mistake. Up here, my eyes weren't working. This was x over 8, was that right? Yeah, that was x over 8. So let me make sure I got, okay, yes. My mistake, f of x was x over 8. It didn't come into play yet, it'll come into play now. Okay. So this is f of u times 1/4, but f of u is u over 8, or u over 32. But remember what u was. U was y plus 2 over 4. So this gives me y plus 2 over 128. So I have g of y is equal to y plus 2 over 128 over the interval. What did I say the interval was before? It was from -2 and 14, and it was 0 elsewhere. I want to do another example. Okay. By the way, this example worked out nicely because we had a nice function. You'll see what I mean by that in a moment. So here, let's consider another example. Let's take the same PDF, okay? So x will have f of x equal to x over 8 between 0 and 4 and 0 elsewhere. And now let's suppose the change of variable, what I call w, it's equal to negative 3x plus 1. So observe when x is 0, y is 1. When x is 4, I get 3 times 4 plus 1 minus 11. So y will be defined between minus 11 and 1. Remember, the same problem here is to find the PDF of y. Okay? And by the way, one question might be, for example, is this as an application, what is E of y? That might be a question. Remind you, I'll do that at the end. Okay, so I'm going to begin exactly the same way. Let's first look to find the CDF of y, which by definition is the probability that y is less than or equal to y. Now let's replace y by minus 3x plus 1. And now we got to be a little bit careful. So if I bring over the 1, I get y minus 1. And remember, what happens when you divide an inequality by a negative number? Well, what happens is it reverses the direction of the inequality. Let me just rewrite this so it looks prettier. If I factor out the minus sign on the right, I could rewrite this as 1 minus y over 3. I factored a minus sign on the numerator and denominator. Now notice, let me take the complement of this, because I want to get back to CDFs. So notice this is 1 minus the probability that x is less than or equal to 1 minus y over 3. So I have g of y is equal to 1 minus, now this is f of 1 minus y over 3. So now if I differentiate this with respect to y, differentiate with respect to y, and by the way, so notice, by the way, the derivative with respect to y of 1 minus y over 3 is minus 1/3. I'm going to need that in a minute. I get the g prime of y, which is g of y. The derivative of 1 is 0. I get a minus sign, and then I get f prime of 1 minus y over 3. And the chain rule says I got to multiply this by the derivative of the inside, which is minus 1/3. So this gives me g of y. The minus signs cancel. I get 1/3. This becomes little f of 1 minus y over 3. Remember, f of x was, what was it, x over 8? So this gives me g of y is 1/3, 1 minus y over 3. So this gives me 1 minus y over 8. Let me just see. Why am I off by... Oh, I'm sorry, my arithmetic was wrong. This 3, so this gives me, of course, this 3 is in the denominator, so I get a 72 here. So I've just shown g of y is equal to 1 minus y over 72 if y is between minus 11 and 1 and 0 elsewhere. So for example, if I wanted to find e of y, that's just equal to y g of y dy as y goes from minus infinity to infinity, which in this case would just be the integral of from minus 11 to 1 y times 1 minus y over 72 dy, or 1 over 72 and now the rest is just some simple calculus. Y squared minus y cubed over 3 from minus 11 to 1, and that can be worked out pretty easily. You should be able to do that very easily, and that gives you the result. Now, I want to point out something in this problem and the previous. The reason everything worked is I was able to solve for y in terms of x. And that happened because we were working with basically increasing or decreasing functions. So I want to generalize this to a theorem. It's called the change of variable theorem. And it works for monotonic functions. I want to use the same notation from the text, but I think I may write it a little differently. Okay. So let x be a continuous random variable with PDF f of x defined on the interval from a to b and 0 elsewhere. Okay. Let y equal to w of x, some function of x, where w is a differentiable function, meaning it has a derivative, and is either strictly increasing or strictly decreasing. That's called a monotonic function. Then the PDF of y, which I'll call little g of y, is going to be, well, I'll write it, I think I'm going to write it a different way. Well, maybe I'll leave it this way for now. I'll change it later. The inverse function of y times the absolute value of d by dy of the inverse function of y. Moreover, if w is increasing, then g is non-zero on the interval from WA to WB. If W is decreasing, then the interval is reversed, as in the problem we just did. Okay. This sounds like a lot, okay? And it's really a very straightforward result. And by the way, I want to indicate, I wrote the result as follows. G of y is equal to f of w inverse of y times d by dy of an absolute value, w inverse of y. Let me remark, if y is equal to w of x, if this is a strictly decreasing function, then x can be written in terms of the inverse function, w of y. So the result really could be written more easily as this is a y, where x is the inverse function. This is sort of the easier way of remembering the theorem. So let me illustrate the theorem firstly on the two examples I just did, okay? In the first example, f of x was equal to x over 8 on the interval, what was the interval? From 0 to 4, right? And y was equal to 4x minus 2. Notice if I solve for x here, x is equal to y plus 2 over 4. Remember, this is what we called w of x. And dx dy is 1/4. So then according to my theorem, the way I've just written it, f of x was x over 8. The absolute value of dx dy is 1/4. But remember what x is. X is y plus 2 over 4. And this gives me just y plus 2 over 128. And of course, the interval is the same as before. When x is 0, when x is 0, y is negative 2. And when x is equal to 4, 16 minus 2 is 14. So notice here, I didn't have to worry about any absolute value because the derivative was positive. In the second example, f of x was still x over 8. But y was equal to, what was it in the second example? Minus 3x plus 1. That means 3x is equal to 1 minus y. X is equal to 1/3 times 1 minus y. And dx dy is equal to minus 1/3. So if I take the absolute value of that, I get 1/3. So now let's remember what the theorem said. The theorem says g of y is equal to f of x times the absolute value of dx dy. And by the way, the interval will now be when x is 0, y is 1. It reverses because it's negative. And when x is equal to 4, y is minus 11. So this is x over 8. The absolute value of minus 1/3 is 1/3. This is x over 24. And now let's remember, this is equal to 1/3 1 minus y over 24, or 1 minus y over 72 as before. So the theorem really makes life very simple. So again, to emphasize, if y is some function of x, and this is a monotonic function, which means its derivative is always positive, or the derivative is always negative, then the PDF of y will always turn out to be this, where x is the inverse function of y. You have to solve for it. And the interval is either if it's increasing, it'll be this way. If it's decreasing, the interval on which y is not 0 gets reversed. So let's prove the theorem. Simple enough to prove. So let's prove it. So the proof in general is as before. G of y is the probability that y is less than or equal to little y. And this is equal to the probability of w of x less than or equal to y. Now, let's suppose w is an increasing function. In either case, I can solve for x in terms of y. So if w is an increasing function, then I know if I take the inverse of both sides, this is what I would get if I solve for x. So I'm assuming now, it's an increasing function. But by definition, this is f of the inverse function of y. So this is g of y. If I differentiate, I get f prime of w inverse of y times dy. And this, of course, is just f of w inverse of y. And by the way, when I solve, I get x equal w inverse of y. Let's not forget that. So in fact, I get the result I want. This is the way I wrote it in the theorem, but I could have written it this way. On the other hand, now suppose the derivative is always negative. Well, I have the same step as before. But now what happens, if it's always negative, it means when I take the inverse function here and I solve for x, the inequality changes direction. We did that in example number 2. That illustrated that. But this is equal to 1 minus p of x less than or equal to w inverse of y, or 1 minus f of w inverse of y. if I take the derivative now, I get minus f prime of w inverse of y times the derivative of the inverse function. Notice though, this is always negative. So I take the negative sign here and put it with the negative sign here and replace this by a positive value. This, of course, is just minus f of the inverse function. This gives me, take the minus sign from here and put it here. That gives me a plus fw inverse of y. And it makes this positive, which gives me the same result as before. Okay, that proves the theorem. So it's really a simple matter. Let's do one more example to illustrate this. Let's suppose, one more time, f of x is 1/8 x on the interval from let's say 0 to 4. And let's suppose y is equal to e to the x. Well, let me judge that. So I'm telling you w sub x in this case is e to the x. So if you solve x equal ln of y, and dx dy is 1 over y. So we know that g of y is equal to f of x times dx dy. Notice that x is between 0 and 4. Y will be between e to the 0, e to the 4, and or 1 less than y less than e to the 4, whatever e to the 4 is, some large number. And y is always positive. E to, I'm sorry, e to 0 is 1, right? Okay. Oops, I lost that. So f of x is just x over 8 times 1 over y, but x is equal to ln of y. And this is over the interval from 1 to e to the 4th power. Okay. So that's the change of variable theorem. It's a pretty straightforward result. Okay. There'll be ample opportunities for you to deal with these. So now I want to go back and I just want to talk about a nice geometric idea. We talked about the uniform distribution in one dimension. So in one dimension, the uniform distribution said the following. It said, if this is a to b, and this is some other interval of length L, the probability that x equals I'm sorry, from, let's say this is C to D. The probability that x is, I'm saying it wrong. One more time. Here's what I want to say. The probability that x lies between C and D is the length of the interval from C to D over the length of the entire interval. So it's sort of the length of the of C to D, the given length over the entire interval, entire length. By the way, if you wanted to prove that, how would you prove that? Remember, f of x is 1 over b minus a. So if you wanted the probability that x lies between C and D, that's the integral from C to D of f of x dx, right? This is a constant 1 over b minus a. So I get 1 over b minus a times the integral from C to D of 1 dx, which is 1 over b minus a, x from C to D which gives me d minus c over b minus a. So, for example, if you knew a train would come anywhere between this 60-minute interval, what's the probability it comes within this 20-minute interval? That would just be 20 over 60, or 1/3. So this is a one-dimensional problem. But now let me look at some geometry. Suppose we're in 2 dimensions, and we have some region in space of area A, and every single point in this region of space of area A is just as likely as any other. So suppose I ask, here's another little region, some region of area little a. What's the probability that I choose a point in this little region? Well, the probability that I choose a point in that little region will just be the area of this region divided by the total area, if it's uniformly distributed in 2 dimensions. So for example, suppose I have a circle of radius r, and I have a bullseye of radius a. And let's suppose I throw darts randomly at this target, and it's going to hit the target. What's the probability I hit the bullseye? Well, it's the area of the bullseye divided by the total area, which would be a squared over r squared. Let's make that a little bit more interesting. Okay. Consider the following example from the text. Suppose I give you the following region. I give you this triangle. And by the way, what's the area of this triangle? Happens to be 1/2, by the way. 1/2 the base times the height. And now let's suppose I choose any point in this triangle at random. And I'm just as likely to choose any point as any other point. Determine the probability the sum of the coordinates is some number t, where clearly t has to be a number between 0 and 1, right? Because if you look at x and y, they're each going to be fractions. Okay. So here's what I'm asking. I'm asking, what's the probability? Well, let me say this a little differently first. So there are really 2 random variables here. Let the random variable x represent the x coordinate. And let the random variable y represent the y coordinate. So, and suppose I call their sum the random variable t, x plus y. So the question is, what's the probability that their sum is less than or equal to, well, I actually have, I didn't ask the problem yet. What's the probability that their sum is less than some number t? For example, t could be a quarter. So I choose any point at random here. Well, notice if I choose any point at random, the equation of this line, by the way, is x plus y equals 1. We all know pre-calculus. I gave you 2 points. You can find the equation of the line. If every single point on this line is x plus y equal t, this must be the point t comma 0, and this must be the point 0 comma t. So every point on this line, the sum of the coordinates is t. And my question is, what's the probability that that sum, that if I choose any point at random, the sum will be less than or equal to t? Well, that means I can choose any point on this line or any point in this triangle, right? Well, if everything is uniform, notice that this is a trivial problem. This is the area of the small triangle over the area of the right triangle. What is the area of this small triangle? It's 1/2 the base times the height, which is t squared over 2. The area of the large triangle is 1/2 1 times 1. So that tells me the area of the small triangle is 1/2 t squared. The area of the large triangle is just 1/2. The probability that the sum of the two coordinates is less than or equal to t will just be the square of t squared. By the way, you remember t was x plus y. Remember, t was x plus y. So the probability that the sum of the two coordinates is less than any number t, where t is a number between 0 and 1, is just t squared. So observe, by the way, that this happens to be the CDF of this random variable t. And if I wanted the PDF, it's just equal to 2t by differentiation. So suppose I ask, what is the expected sum of this random variable? Well, t goes from 0 to 1. It's t times f of t dt. Notice this is 2t squared. So if I integrate that, I get 2t cubed over 3, 0 to 1, and that gives me 2/3. So the expected sum of the two coordinates in that triangle, if you chose any point at random, would be 2/3. That's an interesting question. Okay. If you look at some other examples in the text, I'm not doing those now. I talk about what happens next in the text is I talk about mixed random variables. I'm not doing that in the course this semester, so I'm leaving that out. If you want to read it, be my guest. It's really a lovely examples. You'll see those if you look at Math 4120. We talk about it there. So please do exercise. Please do the exercises in section 3.2, and let me just project ahead right now. So the homework will be in section 3.2. Today's date is today is Monday, the 30th. Then Wednesday is the 2nd. Wednesday is the 9th. Okay. All right. So here's what I propose to do. Next time I'm going to do the normal distribution. And then on the 2nd, I'm going to do the central limit theorem. That will finish the course. I will give you an exam on the 7th. Okay, this will be a review. I think it might actually be our last class. Is that our last class? Yeah, because I think on the 14th, if I remember correctly, I'll look that up. I think this is our final exam. So what I also like to do is I want to give you a review, possibly on Friday. If Wednesday's the 2nd, Thursday's the 3rd. This is a Monday. Maybe on Friday the 4th, it's Friday the 4th, I can run a review. I know somebody had has a class Friday at 11 or something. If anybody else, I could start it earlier. I'll send an email out to all of you asking about that. But I'll have an optional review on Friday sometime. I can either do it when the class meets, or I can do it at earlier, maybe 9 a.m. We'll talk. I'll see what everybody's free for, okay? All right, so again, today is I'm sorry, I'm all screwed up. What's today's date? There's an error.
The 30th.
Today is the 30th, so my days are all off. Hold on. So today, this is today. So Wednesday is the 2nd, right? Wednesday is the 9th. This is the 7th. So this would be the normal distribution. This would be the central limit theorem. This would be, okay, I won't ask, okay, I will do the central limit theorem then, but I won't put this won't be on the exam. I'll have an exam here on the 9th. So the question is, I'll try to run a review sometime on Tuesday, the 8th, 9th. Maybe on Friday, I can have a I can have a review for the final. And then I think the final, I believe, is on the 14th. I will check this and I'll let you know what's happening. But I'm thinking about having a review on Tuesday, maybe around 12:30 on Tuesday, a review, and I can always tape it if somebody can make it. Let me just think about this and I'll send out an email to everybody, okay? Everybody fine with that? So we'll schedule an exam on Wednesday, the 9th. It won't have the central limit theorem, but the central limit theorem will be on the final. Okay, I will firm this up. I'll send it out in an email to everybody, letting you know what we can do, and we'll take it from there. Okay. Anybody have any other questions?
Hey, Professor Kim Lake.
Hold on, give me 1 second to just close some things up here, and I'll take your questions. Okay. Okay. Questions?
Yes, this may be a long shot, but is there a practice exam or something from a previous semester that you could share?
No, I don't have that, but the homework, the practice exam are essentially homeworks. Do the homeworks. That's the best thing for you. I take the exam right from my homework assignments.
Okay, and then for the final exam, I mean, I know we're supposed to know everything, but
Yes.
is it primarily like most of the
It will cover
second-
everything. That is the review for the final exam. A good review would be the 3 exams I had given you, plus extra problems on the central limit theorem that I'll do a review for you as well. And then you just choose problems at random from the text. But the best review to start off with would be going through the 3 exams I would have given you.
Okay.
Okay.
All right. Yeah, thank you.
You're welcome. Other questions?
Hey, Professor Shimron. I came